guys, welcome to our channel of Sciences and Mathematics. Today we're going to look at a concept in mathematics under vectors, and this is going to pertain basically to the concept of multiplication and of vectors. And now under this we're going to look at the concept of the dot product. Then we shall look into details on how we can be able to describe a distance using vectors in a two-dimensional space. Now the concept of vectors is very important because it assists us to visually represent displacement, velocity, and acceleration. These are very basic and fundamental concepts in physics, engineering, and even mechanics. And of course, those finds a wider range of application in our day-to-day lives. So in this case, we're going to discuss a few of these examples and some of the ways in which we can be able to find the dot product of vectors and similar representation. So for that case, thank you and welcome. So as I've said, we're going to look at the concept of multiplication of vectors. In that case, we're going to look at the concept of a dot product. Under that, we're going to also study about the length of vectors in a two-dimensional space. And then we shall look at the concept of Pythagoras theorem. Pythagoras theorem and the distance between 2 points. Under the concept of vectors, and perhaps at the end of this we shall look at a sample question in order to try and figure out how we can be able to practically represent or use these three concepts that we have listed on the board. So in this case, I'm just going to give an illustration so that we can pick up from there. So the last time we said that if we have a point in space P and then there are two rays which are running infinitely in two directions, from this point P, let's say this is ray U, ray V, we do represent vectors using these notations. So therefore, if it's ray for U, this is going to represent a ray, and this is a ray, they are running in those directions. So therefore, if they have a point of intersection at this particular point P, they'll form an angle theta at that particular point. So therefore, we'll call this one the two vectors. Now, in finding the dot product of the two vectors, we're going to use a statement in order to describe how we can be able to do this. Basically, therefore, we're going to have this statement that if U and V are vectors in just write it in full, in two-dimensional space, and theta is the angle between U and V, the dot or Euclidean inner product will be defined by, of course, there are some of the areas in some of our videos that we have mentioned the formula for finding the dot product of vectors and the cross product. So here we're going to mention this formula, of course, from the statement stating that if U and V are vectors in two-dimensional space and theta is the angle between U and V, the dot or Euclidean inner product will be defined by U dot V is equals, we're going to look maybe try to define how we call those two symbols that I've indicated, the cosine of theta. So basically these two symbols represent the noun for vector U and the noun for vector V. Now this condition holds if vector u is not equal to 0 and vector v not equals to 0. Since from basic mathematics that we know that a number that is multiplied by 0 is going to be 0. So therefore, this one can be visually represented as so we are going to represent this vector using this particular figure. So I had said that there's a way in which we can be able to represent this. So this is vector for u, this is vector v, and the angle between them from the step end, as we said, is an angle theta. So therefore we have said that we can be able to represent this one, or the dot product of these two vectors, as the norm of u and the norm of v, the cosine of theta, where theta is the angle between them. So this is going to assist us in finding the length of a vector into space by trying to exploit the concept of Pythagoras theorem. Now suppose we have a figure that is a figure in two-dimensional space, or in that rectangular coordinate, and we have this figure or a particle that is moving in that two-dimensional space. Now that we said vectors can be used to find velocity, acceleration, and displacement, now this have a particle that is moving in that two-dimensional space, and it has two components of its velocity, or two components in which its velocity can be described. Now that vector is going to be represented as such, and we say that one is called the norm. Of course, we're going to see how we can be able to find it. So therefore, suppose we have a length of a vector in two-dimensional space that is represented as such, then the length of that vector, which is from, let me call it its one point OP, then OP is known as the norm, which is denoted as such. So in any case, we try to denote a vector like u, maybe, and v using these particular symbols, and that one refers to the norm of that particular vector. Now from this, we can just try to see that from this two-dimensional space we have created a right triangle, and therefore we can infuse the concept of a Pythagoras theorem in trying to do an analysis of that particular norm, which is represented by the vector. Now by Pythagoras theorem, so by Pythagoras theorem, we know that the vector v can be represented as the sum of the square of the components of velocity v1 and v2, and therefore we can find the norm using the square of the sum of those two components of the velocity of that particular particle that is moving in a two-dimensional space. So this one also can be extended to a three-dimensional space, and we can be able to represent the same using this specific concept. So therefore, we're also going to have an illustration for that using a three-dimensional space. So therefore, I'll draw that coordinate in three-dimensional space, just like that. And this is the point of origin, so that's the x, y, and z component. And then we have a vector that is represented as such. So therefore, in trying to look at this vector in this particular scenario, then we can be able to represent it using now, suppose this vector coincides, or maybe can be described at that particular specific point, and therefore we can say that, just to give these ones for P, Q, O and R. Now let's try to look at this. Suppose we form a rectangular, a triangular figure at that particular point, and this is velocity 1, OQ is velocity 1, QR is velocity 2. Then if we try to look at a triangle OQR, we can be able to describe its sides using Pythagoras theorem, in a sense that this component, as we said, this is the norm of V, and then this is velocity 3. So if we try to look at that, we have tried to extrapolate this particular point in three-dimensional space, and we have said that a particle is at this particular point, and we can be able to describe it using the velocity components for V1, V2, and V3. Now, using Pythagoras theorem, this is a right triangle. Triangle ORP is a right triangle. Therefore, we can be able to describe this OR, since it is an hypotenuse for triangle OQR. OR is hypotenuse for OQR. So using Pythagoras theorem, therefore, we can be able to say that, do away with this. So using Pythagoras theorem, we can be able to indicate that this component squared is the same as OR squared, which is the base for triangle ORP, plus RP squared. So we have described this particular norm using Pythagoras theorem. We can still be able to expand this and say that which is equivalent to OR. For us to find OR, it's the square of OQ plus QR. So therefore, OQ squared plus QR squared. This one is going to give us the square of the hypotenuse for triangle OQR. So therefore, plus RP squared. So the square of this plus the square of this is going to give us the square of that norm. So plus RP squared. Therefore, we are going to find that this is going to give us, if we try to describe this distance in forms of the velocity components that we have used for this, therefore we're going to have V1 squared plus QR V2 squared plus RP V3 squared is going to give us the norm, the square of the norm of those three vectors. So therefore we can as well describe the norm in three-dimensional space using these three components of the velocity by finding the root of the sum of the three components of this velocity. So therefore in two and three-dimensional space we can be able to describe those specific vectors in those ways. And this is going to assist us in describing the position of a particle in a three-dimensional space. I'm going to use one of the illustrations on how we can generally define the distance between 2 points. Now that we have indicated that the distance between OB can be represented using this concept that is derived from Pythagoras theorem, which is of course been illustrated using the three components of velocity in two-dimensional space. The two components of velocity in two-dimensional space and three components of velocity in three-dimensional space. Now let's try to find out on how we can generally find the distance between 2 points, given the components of those vectors in an x, y, and z direction. So therefore, suppose we have a point which is P1, and then we have another point P2, which have been described using the components P1, which is x, y, z, and then we have component P2, which is x2, y2, z2. This is x1, y1, z1 for P1, P2, and P3. So, and this is the distance between them that has been denoted as d. So therefore, we can be able to find the distance or describe the distance d by using the norm of P, P2 as such. So therefore, trying to find the distance, we're going to just use the concept that we have already done by finding the change in x component plus the change in y component square plus the change in the z component square. So this is going to give us the distance between the 2 points, between 2 points P1 and P2 of our vector. So in this case, we're going also to use sample questions in trying to describe this particular exercise that we've talked about. So basically, we're going to do that one in our next video that we're going to do for the multiplication of vectors in handling the sample question. So generally, this is how we can be able to find the distance between 2 points using the concept of vectors that we have described in 2 and 3 dimensional space. So for that case, guys, that is it for today. Let's meet in our next video where we're going to do a sample questions on the same and try to elaborate on what we've discussed. So for that case, bye, thank you, God bless.